In this video, we will discuss atoms. Earlier, we asked the question, what is matter? In this video, we focus on what is matter made of. Atoms. Well, what are atoms? What are they composed of? What are subatomic particles, and how were they discovered? Early work on this question was done by Dalton in 1807. In his theory, there are several tenets. First, all the atoms of a given element are identical. Second, the atoms of different elements have different masses. Third, a compound is a specific combination of atoms of more than one element. And fourth, atoms are neither created or destroyed. They simply exchange partners to produce new things, new matter. So that was the early theory. Now we know there are actually over 100 elements, which in various combinations make up all matter on our planet. Further, we have more direct evidence of what these atoms look like. Dalton pictured them as featureless spheres, like balls. Here is a picture of a scanning, tunneling microscope image of silicon atoms. So silicon atoms as in Silicon Valley, as in computer disks, lots of stuff made out of silicon. So we see they are kind of like circles. So Dalton wasn't that far off. However, we also know there are subatomic particles, and that if we study the internal structure of those atoms, we see how the elements are different and how they're the same. Let's do a quick walk through some history about how subatomic particles were discovered. We start with J.J. Thomson's discovery of the electron using a cathode ray tube. So a cathode ray tube is what is used in old computers, non-flat screens, and old television sets. It basically consists of an electron source and a magnet so that we can have a beam of electrons. And what he discovered in 1897 that these negatively charged particles came from inside of atoms. So he put different metals here as his electron source, energized them, and found that all of them contained negatively charged particles that could be accelerated through this magnet. He also determined or measured the value of the ratio of the magnitude of the electron's charge to its mass, or its charge to mass ratio, and found that it was less than 1,000th that of a hydrogen atom. So he knew these particles were very small. Others were also contributing around the same time, and there was Millikan's oil drop experiment, where drops of oil are suspended between a magnetically charged, positively charged, and negatively charged plate, and then you could view them with a microscope. Millikan determined the charge of an electron using this device and found that the charge of the electron is 1.602 times 10 to the negative 19th coulombs. And we use the capital letter C to indicate coulombs. This, combined with earlier experiments, gives us the charge to mass ratio of an electron. We can determine the mass of an electron and found that it was very small, 9.109 times 10 to the negative 31 kilograms. Also, at the time, since atoms have zero charge overall, where's the positive charge? So we have evidence of negative charge coming out of all atoms that were originally uncharged. Where's the positive charge? So several researchers were thinking about modeling what this would look like. J.J. Thomson thought of it as a plum pudding model, right? Positive charge distributed throughout the sphere loosely, and negative electrons floating around in it like plums in pudding or chocolate chips in a chocolate chip cookie. Nagoda's model was more like a planet, that the positive charge was the center of the planet and the electrons were like the ring around Saturn around it. So these were the current models. So Rutherford students, Geiger and Marsden, were doing an experiment where they had an alpha emitter, which is a positively charged particle, and they were shining this through thin gold, and what they expected to happen is some of the particles would go right through, and some of them would be slightly deflected by the positive charge. However, what they discovered was that some of the particles shot right back towards them. So this was a really surprising experiment. And so Rutherford said, do it again. And so Geiger and Marsden did it again and found the same results. So they had to revise their model. So that's typical in science. We get more information and we are constantly revising our models of how we understand the world around us. So Rutherford's revised model of the atom, instead of the positive charge being diffuse and all around, must be a small, densely located in the center of the atom, which he defined as the nucleus, where most of the mass and the positive charges, and then the electrons are diffusely arranged around it in what we call an electron cloud. So this was the first suggestion of the nuclear model of the atom. Later work showed that the nucleus contained protons and neutrons, so positively charged particles and neutral particles. So here's a summary table of this information. So we have neutrons, given the symbol N, protons, given the symbol P, and electrons, given the symbol E or E minus. Protons have a mass number of 1, as do neutrons. Electrons, since they are orders of magnitude smaller than protons or neutrons, are given a mass number of 0. The charge on an electron is -1. The charge on a proton is +1. And there is no charge on a neutron. So we note this fundamental charge is very similar to what was first discovered by Millikan, is -1.602 times 10 to the -19th coulombs. So here's our current model of the atom. So we have here a gold atom with a nucleus containing protons and neutrons, and it's very small, and there are electrons distributed around it. So our nucleus is on the order of 0.02, 0.01 picometers, whereas the entire atom is 288 picometers, much, much larger than the nucleus. So it's about the size of a fly in a baseball stadium, the nucleus compared to the atom. So we need to have some sort of symbol, because we're not going to be able to draw this picture for every element every time we want to talk about an element. So we have a shorthand way of keeping track of elements and how many neutrons and protons they have. So this is typical arrangement of a box on a periodic table where we have the element symbol. So in our case for gold, the element symbol is AU, and most element symbols are either 1 or 2 letters. Shorthand way of keeping track of it. So AU is for gold. And we have the atomic number on the top for gold. That is 79. So that means there are 79 protons and 79 electrons in gold. 79 protons, 79 electrons. The mass number is what tells us how many neutrons are in the gold. So if I look at my periodic table here, I see that it's about 197 is the mass number. So my mass number, or atomic mass, is protons plus neutrons equal atomic mass. Number. And sometimes different letters are used to distribute that. Often Z is the atomic number and A is the atomic mass number. Depends on what textbook you look at. So let's think about our example here for gold. So if the atomic mass number is 197, if we subtract the number of protons, in this case 79, we will get 118 neutrons. So in this particular gold atom, there are 79 protons, 79 electrons, and 118 neutrons. We'll talk later about how the number of neutrons can vary, which slightly changes the atomic mass number and the atomic mass of elements. To summarize our nuclear atom now, we know that atoms are made up of subatomic particles called electrons, protons, and neutrons. And the number of electrons and protons tell us what atom it is, and the number of neutrons present tell us the atomic mass of that element. The protons and neutrons form a tiny, dense central body that we call a nucleus. And the electrons are distributed in space around that nucleus and take up much of the space of the atom.